Our lesson this week is finding the sum of vectors. Last week you looked at finding the resultant vector using the triangle method and the parallelogram method. And so you're going to use both of these this week whenever you find the sum of these vectors. So let's start with this example. We need to find the sum of vector b plus vector c. So I know that I'm going to use the triangle method here because the way these vectors are aligned. The initial point of C starts at the terminal point of B. So whenever I find the resultant vector, I need to start my initial point at the very initial point of vector B, which would be here at 0, 0. And then it's going to end at the terminal point of vector C. So this black dashed line is my resultant vector using the triangle method, which you did last week. And then all we need to do is write the component form of this vector. So remember, component form, the very first number is your horizontal change, and the second number is your vertical change. So if this vector started at 0, 0, I can tell that it moved right or horizontally 7 units, and vertically or up 9 units. So my resultant vector, or the sum, would be 7, 9. Okay, that's how you look at it graphically. We could also look at this by just adding the components of both of these vectors together. So let's start with vector b. I'll do it in blue. So the component form of vector b would be 6, 5. And then the component form of vector c is 1, 4. So if I were to just add these components together, I would get the vector b plus c, and the component form of that, 6 plus 1 would give me 7, and then 5 plus 4 would give me 9. So this just confirms that we did this correctly, that if we actually add the numbers of the component form together or just use the triangle method, we're still going to get the same answer, 7, 9. Moving on to the next example. This is when you would use the parallelogram method because both of these vectors start at the same initial point. So if we use the parallelogram method, I need to create a parallelogram and then use the diagonal to find the resultant vector. So let's go ahead and start with x, and I'm just going to find the slope of x and then copy it to the opposite side so I can make it parallel. So I can see that the rise over run of x is up 1 over 6. So starting from the terminal point of vector y, I'm going to go up 1 over 6. Alright, and then I do the same thing for y. So if I were to create the opposite parallel side, I can see that the slope of y is going down 8 over 1. So I need to copy that same slope by going down 8 over 1 to create this parallelogram. Now I can do the resultant vector. You start at the same initial point as your original vectors, and then just create the diagonal to find that resultant. So this would be the vector y plus x, or x plus y. So the component form of this black dashed resultant vector would be, let's see, the horizontal change would be 5, and the vertical change would be 9. Okay, let's look at the component forms of x and y just to verify that we did this correctly. So let's start with x. The component form of x is 6, 1. And then the component form of y is negative 1, positive 8. So whenever I add these two together to get this resultant vector, 6 plus negative 1 is 5, and 1 plus 8 is 9. So we just confirmed that we got the correct answer of 5, 9 for this sum. Alright, moving on to another example. They take away your graph and just give you the component forms of two different vectors, and then you have to find the sum. So this one is actually pretty simple. You don't have to graph it or anything. All you need to do is add the component form of each of the vectors to get your sum. So if S is -7, 6, and T is 5, -5, to get the sum, you're just going to add these components together. So -7 plus 5 would be -2, and then 6 plus -5 would be 1. So my sum, if I added S plus T, would be -2, 1, and that's it. Okay, here's another example without a graph. It does look a little bit more confusing because you have the I and the J. Remember that I just goes with the horizontal change. Excuse my handwriting. And J goes with the vertical change. So, same thing. We're just going to add these together. I know B has a horizontal change of 5 and a vertical change of 4. Vector C has a horizontal change of 6 and a vertical change of 6. And then I just want to add them together to get the sum. So the results, if I add these together, for the horizontal change, 5i plus 6i would be 11i. And then 4 plus 6j would give me 10j. So my answer for the sum would be 11i plus 10j. So we're moving on to problems with the graph again. We need to graph R plus S with its initial point at the origin. So you really don't need to graph vector R or vector S. We only want the resultant. If you need to, you could visualize where R and S would be, but the easiest way is probably just to add the components together first and then graph the sum at the end. So if I know vector R is at 7, -3, and S has the component form of 1, -5, I can add those together to get the sum. 7 plus 1 is 8. -3 plus -5 is -8. So my resultant for this sum would be 8, -8. So I have to start at the origin, 0, 0, and then I need to make this vector have a component form of 8, -8. So my horizontal change is +8, so I would go 8 to the right, and then the horizontal change is -8, so I'd have to go down 8. So the only thing you would graph on the IXL is that final vector, which would be R plus S. Okay. Alright, last example. We need to find the sum of vector V plus W. You could use the parallelogram method if you wanted to, or just add the vectors together. So if I know the component form of vector V is -5, 2, and then the component form of W is -4, 6. Once again, I can just add those together. -5 plus -4 would be -9. And then 2 plus 6 would be 8. So my horizontal change would have to be at -9, and my vertical change would be +8. So you don't have to graph it. All you have to do is just find the sum. So that's all you would have to type in. Alright, that's it for this week. Hope you guys have a great week, and if you need any help, please let me know.